Welcome to AP Biology. We're going to go over what to do with non-parametric data today, and then just some of the math skills that AP Biology expects you to be able to do, stuff that just shows up regularly. This first one actually doesn't show up that much, but it's on the list of things that AP wants you to be able to do. So what should we do with non-parametric data? Remember that parametric data has that nice bell curve, and if I look at this picture, it's not parametric. You have a skewing on one side compared to the other. It doesn't look anything like a normal curve. So what should you do with that data? So AP says that you should use a box and whisker plot. I actually have, I don't know, haven't used one of these in a very, very long time. They don't really come up in AP much, but here's the average or the mean, and then you have, I think, quartiles in here. So this is the 50% of the data falls here, and then this is the outer range from one end to another. So that's a box and whisker plot. You've probably used them before. You probably won't use them here, but in case you do, that's what they look like. Okay, median, mode, and mean come up occasionally, especially the mean. And thankfully, you don't have to memorize them because they're on your formula sheet. Mean is the one that we use most of the time. It's the sum of all the data points divided by the number of data points. So we'll go over some examples of these, but we use mean a lot and we use range a lot. So mode and median and mean are all sort of like an average, but they have different meanings, and you've probably done them in math class. So mean is what we use most of the time. Mode is the value that occurs most frequently, and median is the middle value. So we'll do some examples there. Range is going to be the difference between the biggest and the smallest. So I'll show you that stuff. So this is a picture of my family a few years ago. These are my kids and my dad. So my kids at this time were aged 21, 19, 12, and 12. So the mean age of my kids. So I'm going to get my calculator and I'm going to add, let's see, 21 for my oldest plus 19. And then the twins were 12 at the time. So I'm just adding those all up, 64. And then I divide it by 4 to get the average. That's 16. So the mean is 16 years old. And it's always a good idea to put the unit in. And then the next thing is the mode. The mode is the most common one, and so that would be the twins because they're both 12 years old. So that's 12 years. And then the median. So what you do with this is you line up the numbers. So the kids are 12, 12, 19, and 21. And so you just cross out the biggest and the smallest, and you should come up with a number in the middle. In this case, there is no number in the middle really because I have an even number of children. So then I'm going to do the average of those two. So 12 plus 19 divided by 2 is 15 and a half. So the median is going to be 15 and a half years. And then finally, what's the range? Eric was 9 years old when the twins were born. The range is 9 years. And so how do you do that? You do 21 minus 12, and you should come up with 9 for that. All right, calculations. AP very frequently asks you for the rate of something, often from a graph, but sometimes from a data table. So a rate is the amount of change over the amount of time. Calculating it from a graph, you're going to find the slope. So the rate or the slope is the rise over the run. So in this example, it's very linear. So you're just doing the rise. So in this case, it's 8 minus 4, which is 4, over the run, which is 1. And I don't know what the units are, but if I had units on the side, I would have to put them in. Like, for example, if this is, I don't know what it might be, like milligrams or something, and this is time, you're going to end up with milligrams per hour. So anyway, your answer here would be 4, and then you'll do your units of rise over run, your y over your x. All right, so your slope is rise over run, same thing with rate. I haven't seen them ask for instantaneous rate very often, but if they do, let's say they want the instantaneous rate at time whatever, you would go up to your line, and if it's not linear, if it's got this little change to it, you would draw a tangent, and then you would try to do the rise over the run for that tangent line. Again, I haven't seen that very frequently. Okay, what I do see all the time is they ask, what is the difference between something and something else, or what is the, how many times greater is something than something else? So when they ask you what is the difference on some graph, you're going to be, maybe, You're going to be like, I don't know. But think of it in an easier problem. So here's the Wicked Witch of the West. I looked up her age during the movie, and she was only 36, which seems really old to you, but kind of a baby to me. Anyway, Dorothy was 17 years old. So what's the difference in age between them? So you just do 36 minus 17, and that is 19 years. So the difference is 19. Yay? And I'll give you some examples that are going to look a little bit more complex, but really aren't. And then another question that they might ask is, how many times older is the Wicked Witch of the West than Dorothy? So how many times older, you're going to divide that. You're going to say 36 divided by 17. So 36 divided by 17 is 2.1. So she is a little bit more than 2 times older than Dorothy, which you kind of get because, right, double 17 is 34, right? All right, so another thing that they like to ask is write the mathematical steps involved in blah, blah, blah. So this is not a complicated question, but it seems like it. So the mathematical steps in how many times older is the Wicked Witch of the West is 36, and you would write 36 divided by 17 equals 2.1. There are your mathematical steps. For the first one, the difference in age, 36 or minus 17, or 17 subtracted from 36 equals 19, and that's all they want for write the mathematical steps. Okay, next question. This one will look a little bit more like what an AP question might actually look like. How many times more carbon dioxide is produced on average in WT? That usually means wild type, but it doesn't really matter what it means because it's right here. How many times more CO2? So here's the CO2, and if I'm looking at the number here, usually AP will like put little grid marks here so you can tell. I'm thinking this is about 21 picomoles of CO2 per milligram per hour. Okay, so how many times more CO2 is produced in the WT as compared to the amount produced in the gas CCK, KO, whatever that is? So if I look here, the mean is about 6, I think. So how many times more? That's dividing. It's 21 divided by 6. 21 divided by 6 is 3.5. So it's 3.5 times bigger. Write the mathematical steps, and so what you would say is 21 divided by 6 is 3.5. So that's what they are looking for. How much more CO2 is produced on average in this versus this? How much more? Well, it's going to be 21 minus, this number is 6, right? 21 minus 6. That is 15. So the answer here would be 15. And then you can put in your units, p mole CO2 per milligram per hour. Okay. Make sure you do remember to put in the units. And then it says write the mathematical steps that you would need or that would need to be performed. So you would write subtract 6 from 21, or 21 minus 6 is 15. All right. Next question. How much does the histamine release? So this is histamine release. How much does the histamine release increase for mast cells of female rats between 0 p.m. and 100 p.m. estradiol? So here's 0, here's 100. We're looking at females, so I'm going to ignore the triangles. So here the number is 12 and a half maybe. And then at 0, my circle, I'm looking for the circles, which are the females. What is that, 5 and a half? No. Is that 6 yet? I'm going to call that 5 and a half. Again, usually on an AP test, these would be, you have little, tick marks to help you figure out exactly where it is. If you have a piece of paper, use a ruler, because they give you a range, but you do need to get pretty close to the range. So how much does it increase? How much does the histamine release increase? That's a subtraction problem. 12 and a half minus 5 and a half. 7. And I would write 7% of total, I guess. Okay, and then what mathematical steps did we do? Blah, blah, blah. I would write 12 and a half minus 5 and a half equals 7. Okay, next question. What is the percent increase in deaths between 100 and 140 days? So here's 140 and here's 100. what is the percent increase in deaths between 100 and 140 days since fifth total confirmed death for the United States? So 140 is 140,000, and 100 looks like, what is that number? Whoops, what's that number? It looks like 100 and yeah, about here. Yeah, it's a little higher. So 120, 115, I don't know, maybe 116,000, something like that. So percent increase, what you're going to do for that, ooh, I had slightly different numbers, but pretty close. So you're going to do the difference between them, and then you're going to divide it by the amount, like the original amount, so 112 in this case because it increased, and then multiply it by 100. They don't ask that too much, but if they do, that's what you're looking for. So the increase is a difference you're subtracting there, and then you're going to divide it by like the original, the first number, multiply by 100, and um, there you go. Okay, so how to calculate percent change? You're going to do the difference divided by initial times 100, which is kind of what I did on the other side. So how to calculate percent change? It looks like I was looking for the percent change between these, and I know I didn't write a problem out, but final mass minus initial mass, and there's your change. And then you're going to divide it by the initial one, which is this, and then multiply by 100 to get a percent. All right. Last thing I want to do is talk about curves a little bit. So these are just kind of mean curves to show you. They, how should I say this? Just be very, very careful with what the axes say when you're looking at a graph. So milligrams of A remaining, that's like some substance or whatever, and this is probably an enzyme curve, and here's time. So in the very beginning, when you start this, you have 100 milligrams of A. And then in an hour later, you only have about 50 milligrams, and then it doesn't change after that. This one is showing the same exact data, but instead its amount of, it's like sort of putting this rise over run together over time. So milligrams of A used per hour, and doing that over time. So we're using 50 milligrams in the first hour, so that's why we're starting here. So in the first hour, you use 50 milligrams, which you can actually get off this graph, right? 100 minus 50 would be 50 left. So you're using 50 milligrams in that first hour, and then see how it's flat. You're using nothing. That goes down to how much used? 0 milligrams per hour. So these two graphs show you exactly the same thing, but it's displayed in a different way. So be very careful of what you're looking at. One is just milligrams of A remaining, the other is milligrams used every hour. So this one, you can calculate the rate from the graph. This one is showing you the rate right on the y-axis. Okay, the next one, there's time in weeks, progress curve for growth of a pea plant, and then total height. So the pea plant starts out at 0 centimeters over here, and then it's growing, and this is cumulative, so the total height increases, and then until finally at the end around week 4 or so, it's not growing anymore. And then this one is the same data, but it's showing growth rate. So you can see on here that it's sort of growing pretty fast, and it's actually growing really fast around right here. We did this, you might remember this from the ecology unit, where if we look at the slope of this, the slope here is actually the fastest until it slows down and then slows down completely. So the fastest growth, the fastest rate is around 2 or 3 weeks. And actually you can see this here because this is actually giving it to you as a rate on the y-axis instead of having you do a rise over run to get the rate. So again, the same data displayed in a totally different way. So here they're still growing. It's not like you're small. It's not like you've grown this plant and then the plant's getting smaller. It's just that its increase in growth is slowing down by here. And then at this point, it's not that it's a short plant all of a sudden, it's just not getting any taller. Its growth rate has gone to 0, which is actually what you see right here with the flat curve. So again, the same data shown or displayed in a totally different way.